Coral reefs are essential ecosystems that support biodiversity, food security, and coastal communities, but rising sea temperatures and pollution are accelerating coral bleaching and reef degradation. Although underwater imaging with color reference charts offers a non-invasive way to monitor reef health, existing methods still depend heavily on manual annotation and are challenged by underwater image distortions. To address this, we propose Coral-CRCA, an automated multi-stage approach designed to replicate how marine biologists visually assess coral bleaching. This paper was published in 2026 in the Marine Pollution Bulletin Journal. The paper and code URLs are available in the description. Traditional reef health assessment relies on human divers laying fixed transect lines across coral reefs and revisiting the same areas over time. Divers compare coral color to reference charts to estimate bleaching, while software like CPCE helps analyze transect photos by placing random points for manual identification and coral cover calculation. Although these methods are widely used, they are slow, labor-intensive, and often subjective, making large-scale monitoring difficult and limiting how quickly reef health can be assessed. We propose an AI-driven approach that mimics how marine biologists visually assess coral bleaching using Coral Watch color reference charts. The system first enhances underwater images to reduce distortion, then segments the coral colony, isolates the chart regions, and compares coral pixels to reference color grades to estimate bleaching. By combining AI-based Coral Watch analysis with automated coral segmentation, this approach enables a faster, more scalable, and fully automated assessment of large coral image datasets. The data used in this research was collected between 2020 and 2022. 25-meter transect lines were used, and photo quadrants were captured at 5-meter intervals, resulting in 18 photo quadrants per site. In total, the dataset includes more than 3,400 4K images covering 9 different coral species with their ground truth segmentation masks and bleaching percentages. To match variation in coral size across survey areas, we used 3 different configurations: 25 by 25 centimeters, 50 by 50 centimeters, and a separate Coral Watch configuration. Underwater images often suffer from blur and strong color distortion because of how light propagates in water, which makes accurate coral color assessment challenging. To address this, we tested a range of image correction and enhancement methods, including white balance, dark channel prior variance, Clahe, gamma correction, and Rayleigh stretching. We then evaluated how each combination improved color accuracy by measuring the reduction in CIEDE 2000 error, using tuned settings to ensure a fair comparison. To obtain the dominant color from the Coral Watch chart, we first detect the chart quadrants using the YOLO V11 OBB model. We quantitatively evaluate multiple model variants, including nano, small, medium, large, and extra large, to determine which version gives the best quadrant detection performance. Once the quadrants are detected, the pixels inside each bounding box are passed to a dominant color selection stage. The goal here is to identify the most representative color of each quadrant while remaining robust to outliers such as shading effects, uneven illumination, algae, or partial occlusions from other objects. To do this, we compare both statistical approaches, including mean, median, and mode, and unsupervised clustering methods such as k-means, mean shift, db-scan, Birch, agglomerative clustering, and affinity propagation. We then evaluate these clustering methods under different hyperparameter settings, particularly the number of clusters and grid size, to identify the configuration that provides the most reliable dominant color extraction. After segmenting the coral using the Coral-CRCA model, each coral pixel is matched to the dominant colors extracted from the Coral Watch chart. The coral is first assigned to a color group from B to E, and then to a specific shade level from 1 to 6. Once assigned, shades 1 to 3 are labeled as bleached, while shades 4 to 6 are considered healthy, allowing us to generate pixel-level bleaching maps and estimate the overall bleaching percentage. In our evaluation, we compared pixel matching in both RGB and CILAB color spaces with and without denoising. Although some non-denoise settings showed lower error, they were less reliable at detecting bleached corals. Overall, CI lab with denoising gave the strongest and most balanced performance, while RGB with denoising offered a good trade-off between accuracy and efficiency. While our pipeline provides a reliable automated approach for coral health assessment, it still has some important limitations. Because it is based on Coral Watch color charts, the output should be interpreted as a color-based indicator of bleaching, rather than a direct physiological measurement. Performance can also vary across coral species due to natural differences in color, tissue properties, and features like naturally white growth tips. And the method is not suitable for blue or purple corals. In addition, although the system is robust, shaded regions can still reduce accuracy, and the segmentation model is computationally expensive for real-time deployment. Looking ahead, future work will focus on supporting more reef conditions in chart types, adding species identification, improving large-scale environmental integration, and optimizing the system for efficient use on low-power platforms. Thank you for your time and interest. You can find the link to the full article and code in the description below. This work was produced by the Arias Lab, which is part of Khalifa University's Center of Autonomous Robotic Systems. If you found this video useful, please consider liking the video and subscribing to the channel.